but I will do some combinatorics and geometry first. As we will hear on Wednesday, they're totally not related, but let's assume it for today. It's a little bit related. So I want to start with a little bit of motivation. And it's quite simple. So here's a very classical result. You have to do this at the same time. So if I have a graph G, and I know that it's planar, so it embeds into the plane. Then I can say already that somehow, just from this information, that this graph cannot be too dense. It cannot have too many edges. All right. So what do I mean by that? Well, if I have some set of nodes, the number of edges that I can draw between them is bounded, right? So I don't allow cheating like double edges, right? So then I could just draw as many as I want, and I don't allow loops. And then I'm kind of limited in my in the number of edges that I draw. And it's not hard to see. It goes back to basically Descartes and Euler, that the best I can do is I can have, well, it's roughly 3 times as many edges as vertices, right? I just fill in edges until I have essentially, until every region is a triangle, and then there's a basic double counting that, so if I count the number of edge triangle pairs, the edges in the triangle, then I have something like, well, I mean, every triangle has 3 edges. All right, so 3 times 2, t is equal to 2 times the number of edges, and then I have vertices minus edges plus triangles is equal to 2. I mean, I'm looking at the triangle infinity as well, and that's it. Okay, so then I get what this famous bound, and this the number of edges is equal to 3 times the number of the vertices. Okay, and this is a kind of basic bound that is very important in discrete geometry. You can do all kinds of nice things with that. But I mean, if you like geometry, then the first thing that you ask usually is, well, I mean, what happens in higher dimensions? Now, every graph embeds into higher dimensions. All right. So that's not the interesting question. Now you can ask, okay, what happens to if I embed some other objects? And the first other object that you would think about, right? The first other combinatorial object is a simplicial complex. And you could try, okay, simplicial complex into the plane. It's kind of the same question. Simplicial complex into R3. It turns out it's also kind of the same question. Okay, you can solve it using the planar technique. So the first thing that you would be interested in is maybe a 2-dimensional simplicial complex into R4. Right, so generically you don't, the triangles, the top dimensional faces, they don't intersect except for vertex, right? Except for a point somewhere in the middle, right? That's it. So and now you want to make this as dense as possible. And then the next question would be, well, I mean, you have a k-dimensional complex, you embed it into R2k, right? And that's a critical question. And now you ask yourself the same question. Well, how many k-dimensional faces? And this is usually denoted by fk. How many k-dimensional faces can you have? And then the theorem is, and this is quite recent, is that the number of k-dimensional faces, so let's say, let me make the assumption correct, so myself in 18, is that the number of k-dimensional faces of delta, let me make some shot, delta embeds into k, the number of k-dimensional faces is at most k plus 2 times the number of k minus 1 dimensional faces. Okay. There's a technical assumption I need here, and it doesn't quite hold as stated. I have to assume that this map is PL. Otherwise, I don't know it. It's open enough if the map is not PL. Okay, so this is the theorem. it kind of blends combinatorics and geometry, or combinatorics and topology a little bit. But it turns out that the solution you need a little bit of algebraic geometry. You need a little bit of algebra. And I will kind of sketch that, and this will be the motivation for looking at Lefschetz theorems without any positivity structure, without any kind of without any projective variety behind it. Okay, so this is the motivation. All right. So how do we attack this? Well, one way to think about this in terms of, okay, so right, so the first thing that you might try to do is to try to turn this into kind of an abstraction theory question. But here's a problem, right? So to count the number of faces is something about the chain complex at the end, all right? But once I want to look at the homology, this is somehow, okay, so I lose information about the chain complex. And now here's a philosophical idea. Toric varieties are nice because if you think about it, they kind of associate to every single one of these combinatorial faces of every single simplex a torus. All right, so every single simplex kind of gets a non-trivial generated homology. And so now this kind of mixes up the topology and the combinatorics in a sufficiently nice way that you can actually count the faces in terms of the homology. And this is some of the underlying idea. So let me sketch how this goes without actually having to go into toric varieties at all. So let's say, so we have this embedding, right? Delta embeds into R2K. Well, I can forget this R2K. I can think of this as S2K. Okay, so now there's a little PL topology of, 30, 40 years ago, is that I can actually flatten this map on every simplex. And then what I have is that I can think of this delta actually as a subcomplex of a triangulation of the 2K dimensional sphere. Okay, so this here is as homomorphic to the 2K dimensional sphere. Okay, that's it. So now, okay, so now I have this delta sitting inside the thing. And now, okay, so now let's think about this a sphere, a triangulated sphere, in a somewhat more geometric way. So let's say I can arrange this around the origin so that the sphere looks as if it was a complete fan. Okay, so what do I mean by that? So a complete fan is just a collection of simplicial cones that decomposes my ambient area. Okay, so in the case of a 2K dimensional sphere, this would be 2K plus 1 dimensional space. Right, and then my sphere is just, okay, so the intersection with the unit sphere here. Right, this is how I think of fans as spheres and spheres as fans. And I have to be a little bit careful because it turns out most spheres you cannot realize it as fans, but let's stay with this picture for a second, okay? So now I have a fan. Okay, I can make this fan rational. Okay, so this is just, okay, so that's a simple exercise. I can arrange it to the fan is rational, and then I have a toric variety associated to this fan. Okay, then you can look at the cohomology ring, and then, okay, so, but now before I lose you, let me tell you, I don't actually need this all of this. Okay, I can talk about this, about the cohomology ring of that fan without actually ever looking at the variety. And this is a simple construction. It goes as follows. Once I have my fan, so this is sigma fan, and I think of fans as spheres. Okay, so I interchange them. Okay, so complete fan, complete fan. So what I look at is the algebra P of sigma of convex polynomials. Okay, so these are the functions from the fan to the reals that are polynomial, continuous, and polynomial on every single one of these regions. Okay, so convex gives us the algebra of convex polynomials. And you might think already, okay, so this algebra actually contains some information about the combinatorics. All right, so it kind of, you can kind of distinguish different rays. What do I mean by that? Well, let's look at the individual arrays here. Okay, I claim they generate this.
What cone-wise polynomials look like? Like, how should I?
Okay, let me generate all the cone-wise linear functions. Okay, so this is graded, right? It's cone-wise polynomial. I can talk about the degree of a polynomial. So it's a graded object. I will talk now. Let's generate all the linear functions. Okay. So for this, I just say, okay, so if I have a ray, so let's say this ray here, I can associate a characteristic function of this ray. Okay, and this function is, well, it's just linear and non-trivial, so linear non-zero on this ray. All right, it's 0 here, some other non-zero value here, and it's 0 on all other rays. And then so on every of the cone regions, it's uniquely determined, right? Because it's a cone-wise linear function. So if it's 1 here, 0 here, and 0 here, you know it here, right? And this generates, in fact, this gives you all the cone-wise, all the cone-wise linear functions. Okay, so this is now chi r. This is non-trivial on the ray R, and 0 otherwise, 0 on all others, on all other rays. Right? And this actually generates this as an algebra. Okay, not only does it generate the degree 1 component, it generates this whole algebra. Okay, by multiplication. Now, even more, what I can do is, okay, this turns out, okay, so it turns out to contain some information about the combinatorics. Let me delete everything that is boring in combinatorics. Well, what is boring combinatorially? What doesn't tell me anything about combinatorics? It's the global linear functions, right? I don't care about those. They don't tell me anything about the fan structure. Okay, so let me define A of R, or A of sigma, right? And this is the quotient of P of sigma by the global polynomials, global linear functions. Right, so I take the ideal generated by the global linear functions. Okay, and now this object turns out it's a finite dimensional object, right, as a vector space. All right, so this here, okay, if you want to be a commutative algebraist, P of sigma was finite codimension. This here is really a finite dimensional object. In fact, if sigma is now, so if D is equal to the dimension of sigma as a fan, okay, so this is the dimension of a sphere plus 1, right? So the dimension of the Ambiel space, then the top degree, the top non-trivial degree of A of sigma is exactly D. AD, sigma is equal to, well, is equal to the ground field, to the base field. Okay, so that's one basic, okay, so that's a basic fact. And even better, this algebra, okay, it's still graded, right? I took a graded ring and I took out the homogeneous ideal, so it's still graded. I can still talk about the degree of a polynomial. And it behaves, right? I talked about this as if it was a homology ring of the toric variety, so it better behave like it. So in fact, it does. What it does is, for instance, it behaves like it in the following way. It satisfies Poincare duality. So AI and AD minus I. This goes to the GDD component, right? And then I have this evaluation map to the reals. So normally it's called the degree map, but let's ignore that. And this here is a perfect pairing. Here's a perfect pairing. Right, meaning that this is just Poincare duality. Or if you talk to a commutative algebraist, this is what is called Gorenstein property. Okay, this is a Gorenstein. Okay, fine. That's a nice property. But I claim that this has something to do with the combinatorics here. So let's try to estimate the size of this ring. All right, so let's try to give some estimates. And let's focus in particular on this case where D is equal to 2k plus 1. Okay, because this was the one that I wanted to talk about. So if D is equal to 2k plus 1, what I want to look at specifically the size of AK, dimension of AK. Let's look at this first. Dimension of AK of sigma. Well, okay, so I told you that somehow that the degree 1 component, it's generated by the rays. And it turns out that similarly, the degree K component, this is generated by the square for monomials of degree K. And it turns out that these are just the cardinality K simplices, so those cones with K rays, which corresponds to the simplices of dimension K minus 1. Okay, so this is less or equal to Fk minus 1 of sigma. Okay. Now, there's something even more. I can even talk about delta. So delta, right? Delta is a subfan of sigma. It's not a complete fan, but I can still define the restriction map. Right? I just restrict. I take all those converse polynomials on sigma. I restrict them to delta. All right. So A delta, right? P delta. Right. This makes sense. It's as just a small as the restriction of P sigma. Simple enough. All right. And this descends to through this quotient, and the same counting formula holds. So AK, so same with delta is lesser than Fk minus 1 of delta. All right. So this is a simple estimate. I just looked at a space and I wanted to estimate its size, so I found a generating set. Another way of estimating the size of a space would be to, well, I mean, I guess a generating set, and then I try to understand, I try to estimate the number of relations. Okay, where do the relations come from? So let's say, I mean, I take the same generating set, I take the K phase. So right, I cheat because I look at specific spaces already. So AK plus 1, that's the one I want to look at. So I write down the generating set. So here it applies to both sigma and delta. So let me just.
Can I ask one thing about sigma and delta? I mean,
yeah.
If I have something which is, isn't it that P of delta is included in P of sigma because I have a subfan, so I.
Yeah, exactly.
Yeah, okay.
And this map is this is a surjection, exactly. Yeah. Yeah. Just a restriction. Yeah. Okay, so I have this. Okay, so I do the squiggly line because it holds for delta and sigma. So I write down the generators. So where do the relations come from? Well, it's a quotient by an ideal generated in degree 1. All right. So the relations in this quotient, right? They come from they come from the codegree 1, right? Which means they come from the K minus 1 dimensional phases, right? So they come from the degree from the cardinality K phases, right? I'm looking at the degree K plus 1 monomials, and I'm looking at the relations.
Sorry, is that inequality?
Yeah.
Is that inequality?
This is very small. I now have to give an estimate for the number of relations.
Oh, I see.
I haven't done it yet. So it turns out that the estimate for the number of relations is K plus 1 times those phases of cardinality. Okay, this is, I mean, if you think about this purely in terms of, right, I mean, rational equivalence, it's not so easy to figure out, but there are some models that kind of obvious how to get this estimate. Okay. Now, I can see this. I should have started here. Okay. Now this is nice because this nice inequality turns into an even nicer inequality that I have to prove now, right? And what I have to prove now is that A K plus 1 of delta is in dimension as a dimension as an R vector space is in dimension less or equal to the dimension of AK. That's what I want to prove. Right? That's my goal now, right? So this inequality, knowing these two inequalities, I now have to prove this Much nicer than this even, right? Well, this was nice, but this is I don't think it gets even nicer. All right. So now, okay, now we finally get to the Lefschetz property. So we will see it. We will see it in a second. So let's look at this. Okay, this needs to be oiled, or I'm doing it wrong. I don't know. Okay. What do we know about these spaces? Let's look at them on the level of sigma. Okay. So let's look at AK plus 1. All right, Tanian algebra degree k plus 1, but of sigma. Okay. Well, I claim they're isomorphic, and the theorem is actually already on the blackboard. Why? That's Poincare duality. The fundamental class is in degree 2k plus 1. All right, so there's a perfect pairing between them. All right, I should have maybe, okay, so let me write it in this form. But Poincare duality is not good enough for us. Because Poincare duality gives me no way of concluding an inequality like this. Right, so it gives me that these spaces are isomorphic, but it doesn't give me a way to descend this to this quotient of sigma. So what I do instead is, well, I could hope that this isomorphism is actually supported in the ring structure. All right, what do I mean by that? Well, how would I get in the ring from here to here? I would multiply with an element, right? With an element L, where L is in A1 of sigma. If this is an isomorphism, right? If isomorphism, then, well, what do I get? Well, I have these two, and I have AK of delta. That's a surjection. I have AK plus 1 delta. That's a surjection. And then I have the induced map here, which will be then a surjection, right? So isomorphism, surjection. This will give me a surjection here. So if isomorphism, I get a surjection. I get surjection here. And this proves the inequality. Right? If I have an isomorphism, I get a surjection. So now where would this isomorphism come from? Okay. Well, it turns out that it's a theorem. Well, almost. Okay, so let me say why it's a theorem and why then it's almost. So theorem, if sigma is a complete fan of dimension D, so let's say simplicial. I mean, I was talking about simplicial at the time, but let me make it explicit. And L in A1 of sigma is strictly convex. All right, so this would be kind of the analog of ample class. But the point is that, first of all, I don't need that this fan is rational in any way. All right, that's irrelevant for me. The model exists without the toric variety existing. Okay, so there are some constructions for irrational fans. Let's ignore that. So strictly convex just means, okay, so I have a function that is convex, and strictly convex just means that that the domains of linearity are exactly the cones of the fan. Okay, so strictly convex just means that when the fan breaks, somehow, if I go from one cone to the other, then I have to be nonlinear at this point. Okay, so domains of linearity cones of the fan. then we have two properties. Well, okay, so the first thing would be that the Hard Lefschetz property. Then Hard Lefschetz. Which means that I have an isomorphism from degree I to degree d minus I. So I must be less or equal to d half, induced by the multiplication with L to the d minus 2I. Okay? That's the first part of this theorem. And this always comes, almost always comes, with the companion property. So this is a Hard Lefschetz property. And the companion property to this Hard Lefschetz is equally important because usually, I mean, in some way or another, they are proved in tandem or they come out together. And this is the Hodge-Riemann property. So Hodge-Riemann relations. And this is okay. So let me define first a quadratic form. Looking at AI times AI to the reals. Okay, so for this, let's just believe that there's a canonical way to do this identification, right, with sign. Okay, so I go from AI to the reals. So how do I do that? Well, I take A and B, and I send them to L to the D minus 2I times A times B. All right, and now I'm in the top degree. And now, okay, so this is just some quadratic form. That's QLI. And okay, so it doesn't for the minute it doesn't. There's no property, but the property is the Hodge-Riemann relations. Okay. And it's formulated as follows. So there's a certain subspace. So let's say PLAI associated to L and AI. And this is just the kernel of the Lefschetz map taken one too far, right? We're going a little bit too far here. D minus I plus 1, L to the D minus 2I plus 1. All right, so this is no longer an isomorphism. This we usually have the kernel. And this property is that on this space, QLI is definite of sine minus 1 to the I. Okay? Okay, this is a classical theorem. And even somehow in cases that somehow we know this without an algebraic variety, for instance, this case of Bergman ferns or the case of Coxeter groups to Elias and Williamson, in some way these two properties come together. Okay, so this is somehow this is kind of, we can say a lot using convexity, and even if the variety doesn't exist. Okay, so this is beautiful. The problem is that first of all, there are many ferns where I don't have L. It's more, there are ferns where this class L, where there's no L satisfying these conditions. There's no convex core. And if it's not really small, if there are spheres, let's say, for instance, let's go very extremely, let's say sigma is not a sphere that you can realize as a fern because it could be just a homology sphere. Then we don't even know what convex should mean. In fact, you can show that, I mean, okay, so in fact, we can go even worse. We can, I mean, you can have a sphere that is just a sphere over a field of positive characteristics. Right? And then what would you talk about in terms of convex? So there's really no way of I mean, obviously thinking about convexity. So there's no way of talking about ample classes. And so all these nice things that Ramon is, for instance, interested in, like Hodge-Riemann relations, like, or he's interested in Alexander Fencher, which is smart. Right? It follows from Hodge-Riemann relations. These don't exist anymore. So the whole point of this Lefschetz beyond positivity is to prepare this to to find a way to prove Lefschetz properties without having this positivity, without having convexity. And here's let me write down the main theorem, and then I will go into some recent developments that go even beyond this combinatorial case, and I will try to sketch some conjectures. I have some time, so if you please stop me with questions if you want at any point in time. All right. So I guess this is the most old on the blackboard. Oh, there's even a blackboard behind it. Or is it a fake one? All right, doesn't so I confuse it. All right. Okay. So let me first write on the theorem in the case that we knew a few years ago, and then we will go to an even more general case. So here's a theorem. Okay, and I will explain what parts come from where, and then there's Papadakis and Petrotu in 21, and then us together in 22. So let's K be a field. And just for simplicity, let me assume that the field is infinite. Okay. Infinite. And sigma homology sphere. Homology sphere over K of dimension d minus 1. Okay. So let me not go into the definition of what specifically what I mean by this algebra P of sigma over an arbitrary field. Essentially, you can think of this. You can think of this as every cone as living in its own vector space over that field. Looking at the commas, the polynomial functions in this own vector space, and then glue these vector spaces together. It's a little more complicated, but let's keep the picture of the reals in your mind. Okay, so if you want later, I can give you a concrete definition of this algebra P of sigma and A of sigma over any field, but let's ignore this for now. Let's just turn to the reals.
So for homology sphere, do you mean like some PL manifold?
No, it doesn't have to be a PL manifold even. So as long as okay, so you can look at the links of vertices or links of faces, and they again have to have the homology of a sphere.
Okay.
But that's it. Okay, so it's really just a purely homological definition. Okay, so locally, right? So the pole set looks as if it was in terms of homology, looks as if it was a sphere. Okay, let's go to P of sigma again for a second. So if you think about it, I was only trying to encode the combinatorics. All right, but then there are many ways of drawing this as a fan, abstractly or concretely, right? I could have drawn the fan over a pentagon like this, or I could draw this in a much more extreme way, like this. There are many drawings like that, and all these different drawings, they correspond to different. So this does not have different drawings. They don't affect the structure of P of sigma. P of sigma will always be the same, but they affect the structure of A of sigma. They will give different quotients. All right. So if you look, for instance, at the toric variety over this fan and over something like this fan, all right. So these are very different toric varieties, but this is P1 plus P1, and this is the Hilbert deformation. All right, so A of sigma will be very different, P of sigma will be the same. And these different, so these different geometrizations I will denote by theta. Okay, they're parameterized by linear forms over that field. Okay, so basically what I'm doing is just I'm prescribing the global linear functions. Okay, and now what I can do is I can look at all the possible theta that I could choose, and then what the result is the following: if theta is generic, then A of theta and L in A of theta. So I'm now writing theta to just signify this dependent on theta of A of theta sigma is generic as well, is chosen generic as well. Then what I have, well, I have the Hard Lefschetz property. Let me write it here. Then I have a Hard Lefschetz. So AI to a d minus I induced by the multiplication LD minus 2I is an isomorphism. Or maybe I should say something. Let me give a property 0, which is due to Hofstad. And this is that A of sigma is a Poincare duality algebra. Okay. That's okay. So this is a classical theorem. It's Poincare duality satisfied. We have Hard Lefschetz, and then we have something that replaces these Hodge-Riemann relations. And this is a little different depending on which paper you look at. So the Hodge-Riemann relations, they say that okay, so this bilinear form, this quadratic form, this is of a specific sign, a specific subspace. I cannot hope for sign anymore, right? Especially if I'm over a field of positive characteristics. But what I could do is I can hope that maybe at certain subspaces something nice happens. Okay, and the properties as follows. So the first property that was in this original paper from 2018 is what I call the Hall-Laman relations. I will try to explain a little bit where this name comes from. And this says that if I is any square-free monomial ideal, then QLI restricted to this ideal does not degenerate. Okay, so square-free monomial ideals are just those ideals that are cut out by subcomplexes. Okay, so there's a delta, a subcomplex of sigma, and then these are those ideals that I get as the kernels of the form A of sigma to A of delta. Okay, so those are the ideals I'm interested in. And the proof is now the proof of these two properties together. This is rather complicated. It's a rather complicated induction. That where it kind of depends on somehow you prove this in codimension 1 and then you conclude this from it. Okay. I will give you an indication how this works, but it's a very complicated induction that goes by dimension. But then there's okay. So then Stavros Papadakis was a student of Matt Fried, and his student Vasu Petrotu. They looked at this and did it in a much nicer way. And it's a very beautiful theorem with the caveat. In the sense that it only works over characteristic 2 at first, and in characteristic 0 as a conclusion of characteristic 2. And this is the following property. So this is small. I said on subspaces cut out by the combinatorics, it doesn't degenerate. Okay? And what they said, I mean, it's hard to surpass in beauty, and we're kind of still trying to realize this property in full. in other characteristics, but that's kind of one of the beautiful open problems. And this is follows. So let me look at a larger field. Okay, so here I said generic. Generic is kind of okay. It's wishy-washy. I mean, so there's an open dense set of theta you could choose as a parameterization. Okay, but I mean, if it's generic, how do I give explicit coordinates? Well, I go to a transcendental extension and just take the transcendental coordinates. Right? If it's generic, then it works with transcendental. And I tried to make this work when originally proving with this with transcendental coordinates and then doing it like explicitly over transcendental coordinates, and it didn't work. But it turns out that if you just look at this in characteristic 2, then transcendental coordinate is the most beautiful thing that you can look at. So what do I want to say? So let's say K. I look at the field extension, and this is just a field extension of the rational functions over these transcendental coordinates. All right, so this is K tilde for me. Okay, so I look at this field extension. Okay, and now I'm in a new field, and then in this new field, in a sigma, a theta, but now that these theta are somehow independent transcendental coordinates, Q L I R K of characteristic 2. So characteristic of K equal to 2. Over this, QLI never degenerates at no subspace. Okay. Or in other words, for all U in AI that are not equal to 0, all right? If I look at Q L I U U, this is not equal to 0. Okay. So not only do I not generate special subspaces, I don't degenerate anywhere. Okay. It's just like it doesn't go more beautiful than that. It's this is a miraculous property, and there we're kind of there's still somehow. Okay, so what happens in other characteristics? Somehow in other characteristics we have a kind of weaker extension of this, where somehow either this quadratic form does not vanish, or we have some U prime that is somehow has similar support as U that somehow does not vanish. But let me not state that somehow the more ugly version in arbitrary characteristic. What you get in characteristic 0, just as a somehow over the rationals, just as a corollary of a characteristic 2, you get also this total anisotropy. But that's basically the extent that we know in other characteristics. Okay, so question or problem, does this total anisotropy of Q extend to other characteristics, or yeah, to other characteristic, and so I mean the only thing somehow, let me just say the rationals is trivial, right? Corollary of characteristic 2. Right, so this is somehow this is really a very nice problem that we're still trying to understand. Okay, so this is the theorem, and now let me sketch how one proves how one gets the Lefschetz property from this pairing property, from the fact that maybe just pairing does not degenerate as a subspace. But it's kind of obvious that somehow if I have this if I have this property in full, if I have these properties in full, then I get Lefschetz. Right? Lefschetz is obviously weaker than that. But the point is not that we have this immediately. Basically, what we prove first, the first result that you prove is not that that Q and I is non-trivial. The first result that you prove is a little bit weaker. The first result is essentially just that you prove that so idea prove that u times u is not equal to 0. So every element pairs with itself. Okay, this does not necessarily go to the top degree. So just for every element at most half the degree, you just prove that u square is not 0, provided u itself is not 0. Okay. So let me give you the indication on why is it enough to prove that u times u is not equal to 0? How do you construct Lefschetz elements of that? And that's a classical lemma. It is due to Kronecker. Okay, so let's say we have vector spaces, so X and Y are vector spaces over K. So this just, again, this is just any infinite field, and A and B are maps. Linear maps, from X to Y. And what you kind of want to understand is how to construct from the self-pairing property without any L, how to construct an isomorphism. And the construction is rather simple. So what we want to say, okay, so we have A and B, we have these two maps, right? So these are candidates for L that have kernels. They're not quite isomorphisms yet. So what we want is to make the kernel as small as possible by combining the two. So what is the best thing that you could hope for, right? So if I combine A and B, and I want to take not any, I don't want to take just somehow this linear combination. I want to take a generic one, right? Just take a generic somehow. This plus in quotation marks means generic coefficients. Well, the kernel here cannot be smaller than the intersections of the kernels, right? So kernel of A intersection kernel of B. All right, that's what I could hope for. But it's not always true. So what is a nice condition that this is true? Well, I can look at the kernel of A mapped under B. All right, and I can intersect it with the image of A. And these are our subspaces of Y. And if this here is equal to, if this is just the origin, then this property. Okay. So it's a simple linear algebra lemma. Why is it relevant here? Why is it relevant to in algebra? Well, think about it like this. So A is the map that you already constructed, and B is B is just used to mix it up. So B is kind of your hope to kind of increase the genericity. So what am I looking at here? Well, I'm looking at the image of A, and then I'm looking at B times kernel of A. So this is a pullback to B. Okay. This is a pullback along B, and I'm looking at, okay, so if I just had kernel of A and image of A, these are orthogonal complements in a Poincare duality algebra, right? I mean, if I were looking at a Poincare duality algebra, they stand orthogonal on each other. And I'm looking at the pullback to B. These are still orthogonal complements. And I'm asking orthogonal complements to intersect trivially. Right? But orthogonal complements intersecting trivially, that's just saying that the Poincare pairing does not degenerate on either subspace. That's where this property comes from. This is how, once you have this property, you can iteratively construct L by just adding more and more maps here. Okay? that this works out at the end. Again, you have to use Poincare duality, but this is how just self-pairing implies the existence of L. And then you have to show again that L itself, the map here just by L, will also be non-degenerate, and then you can construct L square and so on and so forth. And that's it. This is how self-pairing and the Lefschetz property are related. Now, how does this? Okay, so this is kind of the story, or kind of the beginning of the story, and since then we have been trying to understand actually this property and somehow this total anisotropy. And here's a dream. That's my one dream would be that somehow when could this be satisfied in the most general case? So one thing that we have been looking at recently, and this is a theorem. Okay, let me first give you the setting. Here's another interesting source of Poincare duality algebra, so combinatorial rings that satisfy somehow that could satisfy Lefschetz and don't satisfy it for classical reasons. Okay, well, we don't know it classically. Let me say it. Well, they could satisfy Lefschetz property, but no, don't satisfy it classically. And that is not combinatorial. So what you can look at is a lattice. So let's say lambda is just right. It's just somehow some lattice, and I'm looking at a semigroup in it. So I'm looking at a cone in it. All right. So looking at a cone in this lattice. Let's say this is somehow it's distinguished at Z(-1) times Z. Okay, so I have some distinguished direction for the degree. Okay. I'm looking at this. I'm looking at this cone, and this comes from this cone is what I want to look at is this lattice polytope here at the bottom. So P is this is a polytope generated by lattice points. So this is the cone. K is equal to K of P. The cone over a lattice polytope. So this is a polytope with vertices are lattice points. And now what I can look at is the semigroup algebra associated with P. So I have again K a field, and then I'm looking at P of K, the semigroup algebra of K. All right. What combinatorialists are then interested in is the Hilbert series of this semigroup algebra. If you think about it, this just counts how many lattice points are in P, and then in 2 times P, and in 3 times P, and so on and so forth. So this is what is called Earhart theory. So looking at the dilations of lattice polytopes and counting the number of points inside, this is something interesting for combinatorialists. So it's very natural to count things that are combinatorially determined. All right. Now this algebra you could this algebra is in general not generated in degree 1. It's not a standard algebra. But let's assume that it's generated in degree 1. Let's look at those that are generated in degree 1. So assume that P of K is generated in degree 1. And is Gorenstein. And as well is Gorenstein, or which just means Poincare duality algebra, right? Poincare duality algebra. So these are two kind of central properties. So this here just means combinatorially, if I look at a lattice point in here, right, in the cone, then it's a linear, it's a non-negative lattice combination of points in P itself. So I can write it as a lattice combination. The points here in P, the lattice points in P, they generate they generate all lattice points in the cone. And Gorenstein is again, okay, so you can also formulate it in terms of, this actually has a lot of importance if you look at the mirror symmetry. It basically says that if you look at the polytope P, it's a lattice polytope, and the dual of this polytope is again a lattice polytope. So this is equivalent to saying that the dual of P is again a lattice polytope. All right. And then, okay, so then people looked at the Artinian, in algebra, a quotient A of sigma again, or A of K again, in this case. So A theta of K, this is again the quotient of P of K by some linear forms. So this is what's if you're in commutative algebra, again, you would call it a linear reduction. And they observed that in this case, the following properties seem to be true. If they denote it by hi, the dimension of this this hi of, let's call it P, this hi of K of P in degree I. And they observed, okay, so this is again, it's Gorenstein, and you can kind of already see that this here will be, this means that AI is isomorphic to A d minus I. So it's already palindromic. So hi is the same as hd minus I. So it's again palindromic structure. And they observed that these vectors here seem to be unimodal. So meaning that they rise until some point and then maybe they plateau and then they fall again. Okay, so but they have a peak and they have a unique peak. Okay. And again, okay, so you would think, okay, so if there's a unique peak at least in observation, then this should be explained in some way algebraically. And indeed, the recent theorem of myself, Papadakis, and Petrotu, and my student Johanna Steinmeier is that indeed we have the Lefschetz property. So if K is of characteristic 2, or 0, then A of sigma, A of theta, for generic theta satisfies the Hard Lefschetz property. And this implies that these hi of P are indeed unimodal. And so this was kind of a test case because we wanted to go beyond this combinatorial case and still see whether we could prove Hard Lefschetz with kind of similar methods. It turns out that there are some interesting Parseval type identities. So there's some interesting positive characteristic or characteristic 2 Fourier analysis going on here. I don't know whether I have no more time. So, but you can either force my student or you can force my student to explain, which is good. She's supposed to speak, or you could ask me later. So there's some really interesting things going on. Let me just give you a dream. All right, I'm supposed to talk about dreams on Wednesday, but I will talk about nightmares or ways. I didn't even give you a dream. So what could be the most ideal case, and what is the case I actually want? So this here is kind of the semigroup algebra over an integral domain. What could I hope for? Well, what I kind of hope for is that, let's say I have a standard algebra, so conjecture. Conjecture. So let's say I have a field, so small a K field, and P is a graded commutative algebra. Commutative standard. Standard just means generated in degree 1. Degree 1. Gorenstein algebra. Of positive codimension. And now, okay, so I want to say that a generic Artinian reduction, it's a generic choice quotient by a generic linear form, will satisfy this property. Well, I have to give you one more property that this is reasonable. So I want to say that this is reduced. Okay, so there are no nilpotent elements in this. So for instance, there's this case here of that I talked about, this A of sigma that I talked about, P of sigma is reduced. It doesn't have nilpotent elements. This algebra is reduced. Okay, then a generic quotient has Lefschetz, Hard Lefschetz, and this total anisotropy. Total anisotropy. That's kind of my dream. It's kind of the idea of the most general conjecture that one could hope for, right? So that this generic Hard Lefschetz and this generic anisotropy or total anisotropy holds whenever whenever I'm allowed some genericity and my ring is reduced to begin with. All right, that's it. I mean, yeah, okay. Let me not go into more details. Let me just stop here and.
Are there any questions? Do you have any nice, obviously non-generic counterexamples to this situation?
Yeah, it's right. I actually had drawn it on the post here. If I look at P1 cross P1, right, and if I look at the divisor corresponding to this ray here, right. So if you think about it, okay, so this just corresponds to the function that is non-linear, is linear here, right? Linear non-trivial here, 0 here, 0 here, right? 0 here, 0 here, 0 here. Right. So if I multiply this function with itself, I claim that it's just a restriction of it's just in the ideal of global linear functions, because I could just take the linear function that is linear here, an extension to the linear function here. All right. So it's 1 here, minus 1 here, 0, 0, and then multiply it with the function that is not the characteristic function of this ray here. All right. So it's just this is already 0. So P1 cross P1 is this is a very nice example because it's as a variety. Classically, it's a nice and smooth variety. It doesn't go any better, but it doesn't satisfy the self-product property. Okay. And this, in fact, I mean, if you think about it, this gives you a characterization of the self-product property for these two-dimensional pairs. But okay, let's. Yeah.
So yeah, just a foolish question. I mean, how should I think about this anisotropy thing as being what I would call positivity if I wanted a positive characteristic? That sort of, I mean, it.
Yeah, no, I think it's really different because, as I said, this example here, you have the positivity, right? But this is somehow here you have a convex function. It's more the if I draw the level set, it's just a cross polytope. You have positivity here. but it's not. It doesn't satisfy the self-pairing property. So these properties are a little different. You should think about it as the right replacement of this, the correct replacement, but they are not generalizations of each other. They kind of stand transversal on each other.
Are the characteristic zero, they're not equivalent or something?
No, in characteristic zero, they're not equivalent. That's this example. So this example is somehow here you have convex functions, but it will be not. It will not satisfy this total anisotropy. Okay. What is now, if you think about the statement, if you just want to think about fans and toric varieties, is that let's say you draw a complete simplicial fan. You don't know that this satisfies, that this has an L that will satisfy the Lefschetz property. But what it says is that if you perturb the rays a little, all right, then you will have the Lefschetz property for generic function here. That's the statement. But it's somehow, this does not mean that if you perturb these rays a little, it will have a convex function. In general, it's somehow not having a convex function is kind of stable under small perturbations. Right, over there's, yeah.
I was thinking a much more naive, but I mean, if I have a vector space in characteristic zero and you have a linear form,
yeah,
then saying it's anisotropic and saying it's definite, it's just the same thing, right?
Yeah, but I mean, okay, so you have to be a little bit careful here. This, I'm looking at this over a field extension, right? Somehow it's, I'm looking at, okay, so even if I formulate this total anisotropy with k equal to the reals, I'm not looking at the reals itself for this statement. I'm looking at the field extension of rational functions given by the parameterized by this theta. Okay. So I don't know it actually, the statement, I don't know that it holds over the reals. I know that it holds over the rationals, just because I know that it holds over characteristic 2. All right. Okay.
So Karim, can I ask a question? In the kind of applications you have in mind here, where you're trying to understand dimensions of the spaces AK, right? All you really need is that there is one map that satisfies Hard Lefschetz, right? Because you just need one isomorphism. And so having this generic theory is very useful. You can pick it generically. But in applications of Hodge-Riemann relations, for example, where you do have positivity, often you care about some very specific L that shows up that represents whatever object you're looking at. Are there applications of this kind of theory that you envision where you do care about a specific L? And if so, do you have any hope of being able to characterize which L's actually satisfy the, or is that just not, this is just...
No, I don't actually know how to characterize them, no. I know that now in low dimensional cases, there are nice characterizations of when you satisfy this Hodge-Riemann, this whole amount property, but in higher dimensions, I don't have a nice conjecture. It might be hard to write down explicitly, unless you count transcendental extension as explicit.
Okay.
You might not.
But would it be useful? I mean, do you have a situation like?
I don't know what situation.
Okay, so it's just not interesting in this setting.
No, I just don't know an application. It might be that there is an application, then one has to look into it. But I don't have an application where I need an explicit one for now.
Riemann hypothesis. It's no Riemann hypothesis you need to prove for it.
No, it's just, I mean, he's asking, so I want to say, there are some cases where these Hodge-Riemann relations are not applied with respect to some generic or some arbitrary convex L, but with respect to very specific class, because then there's more, these numbers have combinatorial meaning, the intersection numbers themselves. Because this boils down to things like like log concavity in posets and matroids. And he was asking whether there's a specific in this I mean, now I told you about this generic Lefschetz, whether there are cases where I want a specific Lefschetz, and I don't know. I don't know cases where this is important. That's the question. I don't know whether this is small, whether there's small. In some cases, it's relevant to have a specific L. That's
Let's thank him again.
Thanks.